Hello, my name is Brandon Reese. I develop network algorithms in the Operations Research Department at SAS. In this video, I'm presenting a tutorial introducing network analytics, including the basics about what you can do with networks in SAS Viya, and hands-on demonstrations of using network analytics to improve your machine learning models. My goal is that by the end of this talk, you'll become familiar with various techniques for dealing with connected data in Viya, including some powerful network analysis, optimization, and machine learning techniques. To start things off, what is a network? We define a network as a representation of data using entities and connection. We'll use the term node to refer to an entity and link to refer to a connection between entities. We allow an arbitrary number of attributes to be associated with links and/or nodes in a network. We also allow for directed networks, meaning links imply a direction, and undirected networks, when links don't have an associated direction. For example, if person A and person B are friends, that's an undirected relationship. Now, if person A subleases an apartment from person B, that's a relationship that has directionality to it. When this is the case, it is better to use a directed network to model your data. When is network analysis appropriate? Whenever your data have meaningful connections. This is likely to be the case across a wide variety of industries, since relationships can capture abstract ideas like transactions and hierarchies, but can also represent associations like family and coworker relationships, as well as movements such as routes, paths, and trajectories. These relationships can be modeled as static or time-dependent, and network tools like the ones I will demonstrate today can provide efficient solutions to problems concerning connected data. Sometimes these are problems you should not even attempt to solve using traditional relational database joins. It is far simpler to use a network data model when dealing with data where connections are key. So how do you go from related tabular data to graph data? This is often a non-trivial step with more than one right answer. But as a simple exercise, consider the relational data model of Quora, a public database of academic research papers depicted to the left. In our graph model, depicted to the right, we represent papers using nodes, citations from one paper to another using links, and finally, we represent the content of each paper as attributes on each node. Simple, right? As you work with a variety of datasets, you will inevitably need to define increasingly complex graph data models. But remember, the basic principle of mapping entities to nodes, relationships, movements, or actions to links, and properties to attributes. And you will be well on your way to constructing a cohesive graph data model. We will revisit this Quora dataset when we get to the practical demo portion of this tutorial. Here's a catalog of the many forms of network analysis and network optimization techniques that are available through SAS Viya. There are two action sets, network and opt network, which have some overlap between them. The network action set contains what you need to do many social network analysis and machine learning oriented tasks. The opt network action set includes actions that will solve optimization problems that take network data as inputs. In the upcoming demos, you will see examples of many of these actions. As a brief introduction to machine learning, let's discuss some terminology. The terms supervised, unsupervised, semi-supervised, and reinforcement each denote a specific sense in which you can answer questions about your data, and the type of method you implement is often a consequence of what kind of data is available to you. Methods for all 4 types of machine learning problems are available in SAS Viya. You would use supervised or semi-supervised learning when the question you are answering involves a target variable, often called a label, which is available in your training data. The procedure is supervised if every training observation has a label, or semi-supervised if only some training observations have labels. Unsupervised learning tasks often use associations or clustering techniques that don't require any labels at all. Reinforcement learning is an agent-based approach, often used to train models to do some situational decision-making task. We will see examples of supervised machine learning in the demo portion of this tutorial, and more specifically, I will demonstrate machine learning classification, in which the model is trained to make predictions about whether an observation falls into one category or another. So let's take a look at a common workflow used to put supervised machine learning models into production. On the top track, there are several steps needed in order to develop a model. Sometimes these steps involve manual work, but often they can be done using highly automated processes, as we'll see in the steps of the upcoming demo. Note that iteration is often a part of building a successful model, because insights from a first model building experience can be leveraged to produce improved models in subsequent iterations. Along the bottom are steps taken to deploy the machine learning model. These steps must be automated, and the pipeline that was developed can now be used to draw insights and make predictions about new and unseen data. Next, I'll show a couple standard types of machine learning models, which are implemented using SAS Viya in the demo to follow. Neural network models are very general and highly effective tools to accomplish many machine learning tasks. Here, I show a typical arrangement of computational units called a feed-forward neural network. In particular, this is a multi-layer perceptron. The act of training a neural net includes selecting weights and biases that turn this generic computational recipe into a model that makes effective predictions for your use case. Sometimes this training process is started from scratch. For complex problems, though, it is far more effective to begin with pre-trained weights and biases that were learned over a large quantity of related data, and fine-tuning them using data examples related to your exact problem. This concept is known as transfer learning. In SAS Viya, there are 2 action sets that provide neural network modeling techniques. Those are the deep learn action set and the neural network action set. Decision trees are another type of model that allows classification based on using nested partitioning to split your data observations into categories. Understanding a decision tree is fairly straightforward, and there are fairly simple ways to train using any number of heuristics, examples of which are the Gini impurity or the entropy-based information gain criteria. One widely used extension of the decision tree concept is the ensembling of multiple trees. This is the idea behind the forest model, which contains many trees, each trained according to its own subset of the training data. The overall prediction consists of a vote of the individual predictions of all the trees. The major advantage of forest models is that they generalize better to unseen data because they are far less likely than a single decision tree to overfit the training decisions. The content in the demo that follow will introduce you to the network analytics capabilities of SAS Viya and go in depth on ways you can achieve improved machine learning models when you integrate network analytics into your machine learning pipelines. In the notebooks that follow, I will demonstrate using the Python syntax, but keep in mind that in addition to Python, equivalent APIs exist for the SAS language, R, Java, Lua, and REST. I will walk you through a 4-part demo, which will include an introduction to network, machine learning classification using neural network models and forest models, hyperparameter selection using Autotune, and model refinement using feature importance for selection. First, let's take a look at the Part 0 notebook. This will provide an introduction to network analytics and SAS Viya, and will demonstrate the Python syntax for running network algorithms in the network action set. To start off, connect to Cloud Analytics Services, known hereafter as CAS. To do this, you must import the SWAT library. This library provides the interface for CAS. Then connect to the host and port where your CAS server is running. Next, we import pandas and several helper functions I've written for this tutorial. For convenience, I will show the definitions of the more interesting of these functions as we encounter them, even though we load them up all at once from a Python script. While you follow along with this tutorial, refer to the GitHub link provided with this video to review the code at your own pace. For the first example, I'll demonstrate cycle enumeration. As the name suggests, in a cycle, we start and end at the same node, using existing links to connect the dots. In CAS, everything starts as a table. Note here how we specify the network by providing 2 tables. The first table lists the nodes in our data. The second table defines links by indicating a from node and a to node for each link. Next, we draw a picture using the GraphViz library for Python. So how many cycles do you count? Spoiler alert! If you read the documentation for network, you already know the answer. There are 7. We find them by running the cycle action in the network action set. This syntax indicates that we would like to treat the input tables as a directed graph. We want all cycles counted and returned, and we would like the output to be placed into 2 tables called cycle nodes and cycle links. From the log, we learned that the algorithm found 7 cycles. Here are the first few rows of the cycle links output table. A picture is worth 1,000 words, so let's use GraphViz to highlight the 7 solutions found. Great. Second, I'll demonstrate the centrality action. Centrality is a quantitative measurement of a node's connectedness in a graph. Centrality has major implications for machine learning because naturally, influential actors, middlemen, and hubs of the graph often encode meaningful information about the connected data in question. In the following notebooks, you will use centrality and other algorithms to create features that enhance the predictive performance of machine learning models. Here we create another network from a pandas data frame. Note that the nodes table is optional. In this example, we only provide links. In this case, the nodes are derived from the endpoints of the provided links. Next, we'll run 2 textbook algorithms for measuring centrality, closeness and degree. The results are tabulated in the specified output table. However, centrality is more readily displayed in a picture. In the first picture, larger node size represents higher closeness centrality. In the second picture, larger node size represents higher degree centrality. Now I'll show a third example. What if you wanted to run multiple algorithms against the same graph? It is not ideal to load graph data from CAS tables every time. But this is in fact what happens when you specify the graph using the links equals and or nodes equals options. A more efficient approach is available via the load graph and unload graph actions. When using load graph, the CAS tables are ingested only once, and in subsequent algorithm calls, you can point to an in-memory graph using the graph equals option in lieu of the links equals and node equals options. Here's what an invocation of load graph looks like. We specify the links table once, and then subsequent action calls need only point to the identifier of the loaded graph object. See how we subsequently call two different actions using the centrality action and the shortest path action, each time pointing to a variable containing the ID of the loaded graph. Now we show a picture of the solution computed by the shortest path algorithm. Lastly, you can clean up your loaded graph objects using the unload graph action to free them from memory. Of course, terminating your session also unloads any remaining loaded graphs. Now, let's take a look at the Part 1 notebook. This notebook will introduce you to the data we will be working with and show the steps to build neural net classification models. The first model we train will use existing baseline features, but in subsequent models, we will construct features based on network connectivity to improve the predictive power of the neural network models. The task at hand is document classification. Given the words in an academic paper and the other papers that the paper cites, can we predict the category of this paper? The purpose of this in the following notebooks is to illustrate the improvement we can attain by including network features when building machine learning models. I'd like to note that a recent blog post on a technique called neural structured learning presents a different approach to the same problem, examining the same data set. The network feature engineering method presented here, however, achieves higher prediction accuracy than the graph regularization approach presented in that article. We start by loading the data. The load raw data function implemented here shows the syntax for bringing the data into CAS by first reading the text files into a pandas data frame and then uploading that data frame into a CAS table. The dataset is available for public download and consists of two files. The Cora.content file includes a multi-hot encoded representation of the content of each academic paper. The first column, which we call node, contains the paper ID. Then there are 1,433 word indicator flag columns that equal 1 if the particular word appears in the paper, or 0 if the word does not appear. Finally, the last column, target, contains the category that is assigned to each academic paper. The citation data contains only two columns, from and to, for which each row indicates that the from paper ID has a citation to the to paper ID. Next, I'll show a visual representation of a subset of the data using GraphViz to illustrate which papers cite which other papers. Let's try to manually predict the category of the mystery paper with ID 8617. Using only the fact that the mystery paper cites 3 neural network papers and 2 theory papers, what would be your best guess to the mystery papers category? If you guess that it's a neural network paper, you are correct. This is the sort of intuition that backs the various network features that we will construct for today's tutorial. The next steps to building our models are the pre-processing of the data. In standard fashion, we partition the data into a training and test data split of 80%, 20%. Here's the code to do so. In order to reduce run-to-run variability, we store the partition data and load it again on subsequent runs. 3 tables are produced in result. Content partitioned has all the data from Quora.content, with a flag indicating which partition each row belongs to. Content train and content test contain only the training and test samples respectively. Next, we use the eigenvalue principal component analysis method in the PCA action set to prepare PCA versions of the content tables. This is a common technique that allows you to keep only the components that contain the largest eigenvalues. This means the limited number of selected PCA variables can compactly represent most of the variation observed in the original wide dataset. Here's the syntax for running the eigenvalue action. Note that to maintain disciplined use of the data without leaking information, we define the PCA transformation using only training data. We capture the transformation logic using data step code, and then we apply it to the full dataset using the data step action set. Here, I choose to keep the first 40 principal components. I found that this was sufficient to capture most of the variation represented in the 1,433 word indicator columns. The next step involves preparing the links table. In this dataset, citations represent links. We also join the category labels to the links data tables. This step also represents the disciplined use of data to avoid leaks. We create 2 citations tables. The first, cites train, will be used for training, and the second, cites combined, will be used for scoring. In both cases, we join the citations data with only the known labels, those belonging to the training dataset. The difference between the two is that for cites train, we confine ourselves to citations where both the from and to papers belong to the training set. For the scoring table, cites combined, we include links to and from the test set. However, the test data labels are not used. They're represented as missing in this table. The final pre-processing step is the generation of network features. To do this, you can make calls to the network action set like we demonstrated in the previous notebook. Because I'm about to show a number of Python functions, I will first describe what they do. First, we initialize a nodes table. For this problem, the nodes table will be a copy of the content table since it has 1 node per academic paper. Next, we'll load the nodes and links into an in-memory graph object for faster execution of subsequent action calls. After that, we will add node features by running each of the 4 network actions: centrality, community, core decomposition, and node similarity. After each network algorithm runs, we then merge the new features back into our original nodes table. Finally, the unload graph action will clean up the in-memory graph object. Here are the implementations. Note that action calls to load graph, unload graph, node similarity, core, centrality, and community. The initial copy of the data and merging is done using data step run code action. I will briefly describe the features we are creating using the network algorithm specified. But for a more complete explanation of each algorithm, please refer to the provided documentation links for network. Node similarity is called with the flag vector equals true. This allows us to generate node embeddings, which are a compact, approximate representation of the graph connectivity as a vector space. The vector space will have 10 dimensions as requested. We will include the learned vectors as features in our machine learning models. Core decomposition gives a sense of how interconnected a given node is with its neighbors. A higher core number means that a node is connected to a larger, more dense group of neighbors. I found that it is valuable to look at core number not only for the whole graph, but also for subgraphs. For each subgraph, one per category, we consider only those links that connect a paper of that particular category. We take a similar approach to degree centrality. In this function, we compute the degree for various subgraphs. Here, we can exploit efficient by-group processing. In the first call to the centrality action, we group by the from target variable. This means that we are looking at the degree of links coming in from each particular category of paper. In the second call to centrality action, we group by the to target variable. This allows us to get the degree of links going out to each particular category of paper. Remember, this was what we did in our initial intuitive example. By looking at the in and out degrees by category, we create features that tell the model how many others in each category a given paper cites and how many others in each category cite the given paper. For the last features, we run community detection to organize the nodes into communities. Think of these as highly connected clusters. We provide as features each of the summary statistics metrics about the community to which a node belongs. The last function defined here, add network features, runs all the steps in sequence. To complete the data preparation, we run the add network features on 4 versions of our data. The first version is the training table, including baseline features, which are the word indicator variables from the Cora.content file, and network features based on the training subgraph. The second version is similar, but includes both training and test samples, and uses the entire network to generate features. We extract scoring data from this table. The third and fourth tables are like the first two, only they use the PCA representation instead of the raw baseline features. We've now produced all the variants of training and test data that we will be using in this and the following notebooks. Now the model building begins. In this notebook, we will train neural network models. We use the same architecture that is used in the Neural Structured Learning blog post. A dense net with 2 hidden layers between input and output. We also match the tuning parameters from the article. Note that in the posted run, the article reports 78.1% accuracy for the baseline model and 79.6% accuracy after adding graph regularization. The first model we train has baseline features. In other words, only the word indicator variables from the Cora.content file. In the Python functions here, I show the syntax for defining neural network architecture using the build model and add layer actions in the deep learning action set. Next are the implementations for training and scoring these models using the DL train and DL score actions. Finally, to get a statistically significant result, similar to what is presented in literature for this dataset, I define a bootstrapping function. In this function, we run with many different bootstrap subsamplings of the test data so that we can present the average and standard deviation of our accuracy results. After running the training and the scoring of the baseline model, we see 76.9% single run accuracy. After the 25 bootstrap runs with varying random seed, we get an average of 77.7%. The second model we train has PCA features only. Think of this as a concise representation of the baseline features. After the single run, we observe 74.4% accuracy, and after the bootstrap runs, we get an average accuracy of 74.4%. The third model we train has network features only. After the single run, we observe 84.5% accuracy, and after bootstrap runs, we get an average accuracy of 85.9%. This is significant because the best published results on this data are around 86% accuracy. Moving on to the fourth model, this model we train with both baseline features and network features. After the single run, we observe 86.2% accuracy, and after the bootstrap runs, we get an average accuracy of 86.2%. Lastly, the fifth model we train has both PCA features and network features. After the single run, we observe 88.2% accuracy, and after bootstrap runs, we get an average accuracy of 88.3%. We have now significantly surpassed the highest published classification accuracy results for the Cora dataset. Finally, we call the terminate function to clean up the session. This concludes the Part 1 notebook on network feature-enhanced neural net model building. On to the Part 2 notebook. This notebook will provide a demonstration of building forest models to perform the same classification task we accomplished with neural nets in Notebook 1. I will also give examples of how to use the Autotune action set to select the best hyperparameters for these models. In this notebook, we can skip over the data load and preprocessing steps. They are the same as the ones I demonstrated in the Part 1 notebook. Let's get right into building forest models to make the same kind of document classification predictions we made in the previous notebook. As I mentioned in the intro, forest models are ensemble models comprised of multiple decision trees. The ensembling is based on a concept called bagging. In this type of ensembled model, Each decision tree submodel is trained on a subset of the features and a subsampling of the observations. No single tree is aware of all the columns or all the rows of the training data set. This concept of bagging gives the forest model the advantage of robustness against overfitting. In a classification problem, the overall prediction of the forest is defined to be either the average vote or the majority vote of all the trees. The fact that the model is simply an ensemble of trees, as shown by my cartoon, gives the forest model a second advantage. It is more easily explained and interpreted than, say, a deep neural network model. All that you need to do to understand why a particular prediction was made is to follow a path from top to bottom of each tree, answering the question yes or no to the question at each juncture. One major drawback of forest models, however, is that performance is highly subject to selection of appropriate hyperparameters. These hyperparameters include the number of trees, the maximum depth of a tree, the bootstrap sampling fraction, and many more. Furthermore, it is not straightforward for a non-expert to determine what hyperparameters he or she should use. But fear not. SAS optimization provides the Autotune action set that can systematically determine these model hyperparameters for you. We'll get to that in a moment. For now, consider the forest model analogs of the training, scoring, and bootstrapping methods I presented in the previous notebook. In this case, we use the forest train action in the decision tree action set, but otherwise the training is very similar. In the score forest model function, for the sake of demonstration, I show how to invoke the score action in the AStore action set to score your forest model. AStore is a format of representing your data scoring steps that are universal to SAS Viya. Note that we could just as easily have scored using the decision tree .forest score action instead. We define bootstrap runs here in largely the same fashion as we did in Notebook 1. Now, we begin by training the model with baseline features. Note that we are not specifying specific hyperparameters for the forest model. For lack of a better starting point, we will run with the default hyperparameters for this first round of modeling. On a single run, this model gives 43.4% accuracy. After the 25 bootstrap runs, we get an average accuracy of 43.4%. Next, we train a forest model with PCA features. On a single run, the accuracy is 44.1%. After the bootstrap runs, the accuracy is 44.6%. Also, I'll mention a major advantage of the PCA features model over the baseline features model. The PCA model training takes under 2 seconds. This requires significantly less computation time than training the baseline forest model, which takes about 30 seconds. This time taken to train the model is roughly proportional to the number of features we're putting into it. So any tricks we can use to represent the information that is in the training set more concisely will yield a computational improvement. You'll see more on that in the third notebook. Now for the forest model trained on only network features. The single run accuracy is now 80.8%, and the average over 25 bootstrap runs is 80.6%. a significant improvement compared to the accuracy achieved when using the baseline and PCA feature sets. This large gap is partially explained by the extra information provided by the citation network connectivity, but it is also largely a result of poor hyperparameter tuning. We'll see in the next section that the baseline and PCA feature models are more severely hampered by the ill-chosen hyperparameters than the network feature-enhanced models. Next, we train the forest model using baseline and network features. The single-run accuracy is 74.2%, and the average over bootstrap runs is 73.6%. Lastly, we train the forest model using PCA and network features. After we train, the single-run accuracy is 79.2%. And the average over 25 bootstrap runs is 79.6%. These last two configurations were most likely also hampered by poor hyperparameter tuning. With properly chosen model hyperparameters, we should be able to train better forest models. Fortunately, Autotune can help us here. Even without much theoretical expertise or experience tuning this particular type of model, fairly straightforward use of the Tune Forest action in the Autotune action set will help us achieve much better prediction performance. Autotune works by trying many different tuning configurations in a systematic way. The implementation is a thread and machine parallel one, which makes for an especially fast tuning process with access to a computing cluster. By default, Autotune will perform a search of the hyperparameter space using a genetic algorithm and will terminate after convergence occurs or a fixed number of iterations is reached. Also by default, Autotune will take our training data and internally split it into a train validation partitioning. Because Autotune has some fairly smart behavior by default, and because the user may not have expertise configuring this tool, it is usually a good idea to start off with the default settings and customize things from there. Here is the function definition for auto-tuning with the Tune Forest action. As you can see, it is just as simple as the forest train action. We'll keep everything in Autotune to the defaults, except we'll provide our own random seed for reproducibility, and we'll use misclassification error as our objective. We choose this objective function because what we care about in the end is accuracy, which is just 1 minus misclassification error. Note that since auto-tuning can take some time, we would be wise to save the outputs to file so that we have our champion models saved for easy later reuse. We will now run Autotune to produce forest models for the PCA features only. After that, we'll do the same for the network features only and for the network and PCA features combined. For the first configuration, PCA features only, Autotune takes just under 2 minutes. When we score the model, we see a single run accuracy of 68.8%. After we run the 25 bootstrap runs, we get a bootstrap average of 68.8%. That's a hefty increase from the 44.6% we saw without Autotune. Next, we auto-tune the forest model with network features only. The tuning takes about 77 seconds. On a single run, the prediction accuracy is 85.2%, and the bootstrap average over 25 runs is 84.5%. This result also shows improvement over the 80.6% we saw before using Autotune. Last but not least, we train the forest model with PCA and network features, which requires just under 3 minutes to tune. For the single run, 85.2% accuracy is measured. When averaging the bootstrap runs, we get 84.8%. This represents a 5% higher accuracy than the 79.6% that we measured before selecting our hyperparameters with Autotune. So if you learn anything from this portion of the tutorial, remember this. Forest models can be very good predictors, but can also be tricky to tune. The usage of both network features and Autotune have the potential to significantly improve model performance. And of each of the model configurations, the network features model appears to suffer least from inadequate hyperparameter tuning. This is likely because properly engineered features tend to require less intricate decision logic to make good predictions. This is an important corollary to the general concept that models with fewer features tend to generalize better. Finally, we call the terminate function to clean up the session. This concludes the Part 2 notebook on network feature-enhanced forest model building and hyperparameter tuning using Autotune. Moving on to the final notebook, Part 3. This notebook will focus on feature importance methods and using them to construct lean models. A seasoned veteran data scientist once told me that in all his experience, he had never built a model that he could not reduce to no more than 10 to 12 features. He went on to make the controversial claim that if your model is trained on hundreds or even tens of features, you probably still have more work to do. While we're not going to get into whether that claim is true in general, in this notebook, we will at least test this theory for our Cora academic paper classification task. To achieve our goal of building lean but high accuracy models, we will follow a simple approach. First, measure feature importance using 3 different methods. Then, retain only the top 12 most important features according to each method. We will be measuring feature importances in our most effective forest model, the one that combines PCA and network features. In that model, we used 40 PCA features and 45 network-generated features. In this notebook, I'll be showing one tried-and-true method for obtaining feature importance, but I will also be demonstrating 2 brand new approaches as well. Once again, we will skip over the data load and data preprocessing. They are identical to the code we looked at step by step in the Part 1 notebook. Next, let's load the best performing forest model from Part 2 to get a closer look at the best forest hyperparameters that Autotune found for us. We print them out here. Next, we will retrain a model with these hyperparameters. We do this so that we can use the built-in feature importance calculation by setting the flag var imp equal to true. Once again, this is the definition of the train forest function. Note that this time, instead of running with defaults, we now have the hyperparameters that were chosen by Autotune. This time, we will traverse the branch of the code that sets each hyperparameter to the following value. We also indicate, using the var imp flag, that we would like the forest train action to also compute the Gini importances for each feature. Now, after printing out the top 12 features according to the Gini split-based criterion, we see right away that the core decomposition features and the first few principal components were considered important for training this model. Also mixed in are n degree from links in the genetic algorithms category and the 10th principal component. I'm denoting this feature importance method as split-based Gini importance so that I can distinguish it from the new method I will describe later. In split-based Gini importance, we consider the tree split by split. To get a feature's importance score, we add up the Gini gain found at each of the splits where the model chooses based on that feature. Without going into too much detail, I will now describe two new ways to quantify feature importance for tree-based models. Both of these methods have a patent pending. The first method, called betweenness importance, is fairly straightforward. In network theory, betweenness centrality is a metric for how often a node is on the shortest path between a pair of terminals, or endpoints, when considering the shortest paths between all pairs of terminals. In the betweenness feature importance method, the betweenness centrality of each node in the tree determines the contribution of that node. And the importance score of a feature is simply the sum of contributions for all nodes where the model chooses based on that feature. The rationale behind this method of measuring feature importance is that decision tree and forest models are actually just networks that we can analyze like any other network. Betweenness lets us measure which nodes in a network are important gatekeepers to the flow of information. In this case, high betweenness is analogous to high importance in the network of decision-making rules represented by the tree. Now let's look at the top 12 features ranked by betweenness importance. Again, we see that the core decomposition features and the first few principal components were considered most important, albeit this time they appear in a different order. Now let's move on to what I call leaf-based Gini feature importances. This idea is different from split-based Gini feature importance in that instead of finding Gini gain split by split, we instead calculate Gini gain subtree by subtree. For a given subtree, we use the difference in two subtree variants to find the gain. The original subtree versus the subtree with the root node replaced by a trivial node. The intuition behind this way of measuring importance is that if a feature is important to the decision logic, its replacement will detrimentally affect the Gini impurity score. Take a look at the top 12 most important features chosen by leaf-based method. This time, core decomposition features are again considered important, but only 2 PCA features appear in the top 12. They got bumped out in favor of additional features based on degree. Just as a summary of the top features chosen in each of the 3 methods, we find the differences between all 3 top 12 sets. We find that the leaf-based method chooses n degree for the rule learning and case-based categories, whereas the other 2 methods do not. Instead, the other 2 methods, split-based and betweenness, include the PCA components 1 and 10. In fact, the betweenness and split-based methods choose exactly the same set of 12 most important features. We will now attempt to build models using only these sets of 12 features. Remember that for both our neural network model approach from the Part 1 notebook and our forest model approach from the Part 2 notebook, the best performing models use a total of 85 features, 40 coming from principal component analysis and the other 45 coming from various network algorithms. Let's see if we can achieve similar accuracy when we use only 12 of them. First up, we'll try the feature set found by both the betweenness and the split-based Gini feature importance methods. When training the neural network model, we feed the deep learn action set the same hyperparameters as before. After training, we see a single run scoring accuracy of 88.0% on our test data. 25 bootstrap runs later, we find that the average accuracy is 88%. Moving right along, let's train forest models, first using the default hyperparameters of the forest train action. After training on this feature set, the single run accuracy is 79.1%. After the bootstrap runs, we see that the 25 run average is also 79.1%. Next, we'll train the forest model, but this time with the best hyperparameters chosen by the Autotune action set from the Part 2 notebook. The accuracy of one run is 86.3%. And after the bootstrap samples, the average accuracy is 86.4%. Now, let's repeat the analysis with the top 12 features as selected by leaf-based feature importance. For the neural network model, we see a single run accuracy of 87.6%. And after the bootstrap runs, we obtain an average accuracy of 87.1%. Now for the forest model, trained with default hyperparameters. The accuracy on one run of the test data is 79.3%. After the 25 bootstrap runs, the bootstrap average accuracy is 79.1%. And now, the forest model with auto-tuned hyperparameters. After we train the model, the single run accuracy is 87.1%. And after running 25 times, the bootstrapped average accuracy is 85.8%. Last of all, we call the terminate function to clean up the session. This concludes the Part 3 notebook on feature importance methods and constructing lean models. Let's summarize the models that we have trained and consider both the performance of each model in terms of accuracy and time required in training for each variant of model presented in this tutorial. We trained two types of model, neural network and forest models. For the neural network model, based on others' prior work, we already knew an effective architecture to try, the multi-layer perceptron with two hidden layers, and we already had a decent set of hyperparameters that gave very nice accuracy performance out of the box. Roughly 78% on our baseline feature set. This baseline set of features consisted of 1,433 binary flag variables, each of which correspond to a particular word, and the flag variable is equal to 1 if the paper contains the word, or 0 if the word is not used in the paper. The same baseline feature set proved difficult for the forest model when using the algorithm default hyperparameters. The first feature engineering technique we tried was principal component analysis in order to reduce the dimensionality of the training data and also to remove some of the superfluous noise-dominated variation from our input feature set. We found that keeping only the first 40 principal components, we obtain largely similar accuracy performance while considerably simplifying the models. Another beneficial side effect of this change was reducing the time required to train either type of model. In fact, we see that there is generally a direct variation between the number of features we feed to a model and the time it takes to train that model. This is true for both the neural network and the forest models. The next step, which led to significant improvements in accuracy, was creating features using 4 particular network analytics algorithms in the network action set: centrality, node similarity, community detection, and core decomposition. This provided a major lift in model accuracy, primarily because, together, these features serve to encode the structure of network connections given by the known paper-to-paper citations. The next 2 feature sets we tried were combinations of the baseline or PCA feature sets with the network features. And this is the typical usage pattern in most applications. We look to improve a model by supplementing the already available feature set with new features that we generate from network analytics. For the forest models, we found that we could do better by selecting better hyperparameters. As a systematic and straightforward way of selecting good hyperparameters, I demonstrated the Autotune action set, which produced roughly 24% lift in accuracy for the PCA features model, and roughly 4 to 6% lift in accuracy for each of the network enhanced feature sets. For the last 2 feature sets, we combined a bit of innovation with the old-fashioned adage, less is more. I demonstrated 3 ways of quantifying feature importance based on a tree-based model, and then we repeated our training and scoring process with only the set of 12 most important features. And upon examination of the results, we find that there is little to no degradation in accuracy performance when we restrict each of our models to the 12 most important features. This is huge because not only does shrinking the feature set reduce computational costs to train these models, it also results in models that are less likely to overfit to our training observations and therefore are better able to generalize to new and unseen observations. One last benefit of a lean model is that by examining a small number of features, we really understand better what the model is doing and why it performs as well as it does. I reviewed publications that report prediction accuracy for document classification against the same Cora dataset. The state of the art at the time of this presentation was roughly 86%. With the methods shown in this tutorial, we are able to fairly quickly build a forest model that is comparable to and neural network models that surpass the best known published work to date in terms of accuracy. A key benefit of this method of using network-enhanced features to improve your machine learning models is explainability. To explain where your model features come from, you need only describe your data as a network and describe the network-related metric or metrics you are using. And in practice, any network algorithm that produces per-node attributes, like the ones listed here, can potentially encode useful information about your network data. When you have connected data, try experimenting with these algorithms. Each is available in the network action set to improve your classification models. In closing, I want to emphasize that network techniques, Autotune, and effective feature importance, ranking and selection techniques can be formidable assets in each phase of your model building process. Each piece has been demonstrated in the code in this tutorial. Thank you for taking the time to view this tutorial. I do hope it makes the process of incorporating network into your machine learning pipelines easier. And be on the lookout for the latest new features and enhancements coming to the SAS Viya platform.